So now we'll discuss the third Maxwell equation, that is Gauss law in magnetism. You see, something weird happens in magnetism. So a magnet always has a north pole and a south pole sticking to each other without ever detached. Even if you break the magnet, the moment you break the magnet, so there is a north pole here and there is a south pole here. Okay, the moment you break the magnet, again there will be a south pole developed here and there is a north pole developed here. It means that if you take any Gaussian surface around a magnet, then the net flux is always zero. So why the net flux? Because we assume that flux comes out of the north pole, like flux coming out of the plus charge, and flux ends on the south pole, like the flux ending on the negative charge. You see, since the north pole and south pole, they can never get separated, it means inside a Gaussian surface, the presence of both makes the total flux zero. So what can I write? So the Gauss law in magnetism says that flux per unit volume for a magnetic field is zero. Either I can write this, or I can also say that total magnetic flux around any Gaussian surface ds, okay, is zero. So you can convert this into this. Remember how you can use the Gauss divergence theorem. So this is our Maxwell's third equation, that is Gauss law in magnetism, which says that magnetic monopole does not exist. Okay, because always there is a north pole and south pole. If there were individual north pole, then we could have done something. But since north pole and south pole are not individual, but they are always sticking together, so the net flux is always zero for a magnetic field, whatever it is. Then comes Faraday's law. Agreed? So Faraday found an interesting thing, as we have discussed earlier, that if you take a circular wire and if you have a bar magnet with a north pole and a south pole, okay, now the moment you bring the bar magnet near or you take the bar magnet away, there is a current that is generated in the circuit. So we already discussed this Faraday's law in our lectures behind in the CD, and let me write the consequence directly. The consequence is that if there is a current generated in the wire, it means there has to be an EMF generated in the wire. Now, if there is an EMF generated in the wire, it means there is also an electric field generated in the wire. And what is the nature of this electric field? This electric field is circular in nature. See, if the current is flowing in the wire in a circular manner, obviously it means the electrons are being pushed by a electric field which is also circular in manner. So the electric field produced by the changing magnetic flux is by nature a rotationary electric field. So it has a curl. So what was the Faraday's law? Faraday's law say that the amount of EMF generated in a wire is equals to the rate of change of magnetic flux. So this was Faraday's law. So if you change the flux through the wire very fast, then more current will be generated, that is in turn more EMF will be generated. And if you make the magnetic flux passing through the wire less, then less current will be generated. Now, so what is magnetic flux? Like we discussed the electric flux, the magnetic flux is described by integration, surface integration B dot dl. So this is how the magnetic flux is described. Agreed? Now, so if this is true, then what is my E? E is actually a potential. So every potential can be written as a line integral of a field. So my E can be written as integration around a particular curve E dot dl. Okay, it can be written as a line integral, that is E dot dl. Now, so these are vectors. So what is E? What is small e? Small e is like a potential. Always remember, small e is like a potential. So remember how electric field, so your electric field was related to minus of gradient of potential, and in the same way the potential can be written as an line integral of the electric field. So this is the nature of the potential. Okay, so this is, we already know, this is something you already know. So let us focus on this equation. So what does the equation become in both side? In both side I can write the following. I have integration around a curve E dot dl, and this side I have minus, taking d by dt inside, so I will have a surface integral. Okay, d b by dt, so let me write del b by del t into ds. Agreed. Now as you know, one side we have a line integral and the other side we have a surface integral. So by Stokes theorem we can convert this particular integral into a surface integral. So how to do? Via a cross product. So this can be written as surface integral, take the cross product del cross E. Now remember, here we can take the cross product of the electric field because the electric field generated by the changing magnetic field is itself rotatory in nature. It means it is a field which has a curl. Any rotating field has a curl, as I discussed earlier. So this particular electric field here has a curl, and the electric field generated by a stationary charge is a diverging electric field, so it has no curl. Now you can easily equate the LHS and RHS. So what is your last Maxwell equation? So your last Maxwell equation is, that is the fourth Maxwell equation, can be written as your del cross E, okay, is equals to minus del B by del T. Agreed? So this is the fourth Maxwell equation. You see, again let me emphasize the points. What Maxwell did, Maxwell just converted all the integral form of equations into the differential form. So let me write all the Maxwell equation all together. So these are the famous four Maxwell equations. So these are the famous four Maxwell equations. So first law is the Gauss law. Second law, this one is the Gauss law in magnetism. This is Ampere's circuital law, and this is Faraday's law. Agreed? So once that you have generated the Maxwell law, we'll look at its power. But Maxwell did a slight modification to the third law. I mean, it made a slight modification to the Ampere's circuital law. So Maxwell found out that this law is not completely correct. Maxwell found a discrepancy, and Maxwell, to tell what is the problem, Maxwell gave us a very beautiful experiment. So in the next lecture we'll see what problem that this particular equation have, that we'll find out.